As we've already seen in this chapter, there is a striking resemblance between formal logic and set theory. And the text has a beautiful table of those comparisons on page 415. I did not include those in the notes. You can look them up yourself in the text. In fact, the thing is about our logic and our sets, those properties are both special cases of the same general structure, which is called Boolean algebra. So in this section, we're going to learn how to derive the various properties associated with Boolean algebra from a set of 5 axioms. So let's see what our axioms say. A Boolean algebra is a set B together with two operations generally denoted with a plus and a multiplication, such that for all A and B that are elements in the set B, which is our Boolean algebra, A plus B is also in the set, and A times B is also in the set. And generally in Boolean algebra, the addition is the same as an or a disjunction in logic, or a union in sets, and the multiplication is an and, or a conjunction in logic, or an intersection in sets. So if we look at how what we know from logic and sets apply here, we can see some of these axioms make a lot of sense. So first we have the commutative laws. The commutative laws say that for all A and B that are elements in our Boolean algebra, A plus B is the same as B plus A. A or B is the same as B or A. A times B is the same as B times A. A and B is the same as B and A. Sounds awfully familiar. Associative laws say for all A, B, and C that are elements in our Boolean algebra, A plus B plus C is the same as A plus B plus C. And the same can be also said from our multiplication here, our ands. Our distributive laws say for A, B, and C that are elements in our Boolean algebra, A plus B times C is A plus B times A plus C. So this is a little bit different maybe than what you're expecting. It says A or B and C. It's the same as A or B and A or C. And we may have actually proven that one earlier in this chapter with sets. The same can be said if we switch around the multiplication and addition. A times the quantity B plus C is the same as A times B plus A times C, or A and, in parentheses, B or C is the same as A and B, or A and C. Our identity laws say that there exists some distinct elements 0 and 1 that are in our Boolean algebra such that for all elements A in the Boolean algebra, A plus 0 is itself. So A or 0 is A. And A times 1 is A, which sounds a lot like algebra. A and 1 is A. Our complement laws say for all elements A in our Boolean algebra, there exists some element A with a bar over top, which we call the complement of A. Notice it's with an E, not an I. We're not trying to say nice things here. We're trying to find the opposite side. So call the complement of A such that A plus A complement is 1. Well, this sounds a lot like when we were looking at Venn diagrams where we took a set A plus its complement and we got the universal set. Sounds pretty similar. So A or A complement is 1. A and A complement is none. It is the null set. Oftentimes the way we can think of Boolean algebra in relation to sets is if we see 1, we can think of the universal set. If we see a 0, we can think of the null set. And this will make a lot of the Venn diagrams make a lot of sense, and you can go back and see why some more of our arguments were true if you were able to work through them algebraically using Boolean algebra in chapter 2. Kind of nifty how useful these guys would be. They become very, very useful, especially when you get into things like logic circuits. But there are a lot more applications that we're just not going to have time to get into, but I highly suggest, especially if you're in computer science or computer engineering, that you look into a little bit more how you're going to use Boolean in your logic. So these axioms also lead to properties of a Boolean algebra. So if B is our Boolean algebra, we could say that the uniqueness of the complement laws say that for all A and X in our Boolean algebra, if A plus X equals 1 and A times X equals 0, then X is equal to A's complement. The uniqueness of 0 and 1 says, for all A in our Boolean algebra, if there exists some X in our Boolean algebra such that A plus X equals A, then X has to equal 0. And if there exists some Y in our Boolean algebra such that A times Y equals A, then Y has to equal 1. The double complement law is very similar to the one we saw also in sets, where it says that for all A in our Boolean algebra, A's complemented is just A. So we saw that definitely earlier on in chapter 6. Our independent laws say that for all A in our Boolean algebra, A plus A equals A, and A times A equals A. These are going to be very important along with your distributive laws for our discussion post this week. Right, you're going to want to spend a little time remembering that A plus A equals A and A times A equals A. Likewise, you'll want to know that A complement, these guys down here are De Morgan's laws. We're going to be looking at those again too, their complements. So let's scroll a little bit and see what some more of these properties are. Our universal bound laws say that for all A in our Boolean algebra, A plus 1 is equal to 1. A times 0 equals 0. And again, this comes down to a set A or the universal would be the universal, because the universal automatically includes A. A and the null set can only be the null set, right? A and the null can only be the null. So that one makes a lot of sense. De Morgan's laws say for all A and B in our Boolean algebra, the complement of A plus B is equal to the complement of A times the complement of B. We may remember this one as not A or B being logically equivalent to not A and not B. Likewise, if we have not A and B, that was logically equivalent to not A or not B. And remember here, our ors are adding and our ands are multiplication. So it all works out together in the end. Our absorption laws say for all A and B in our Boolean algebra, A plus B times A is just A. And A plus B plus A is also just A. The complements of 0 and 1 make a lot of sense if you, again, make them analogous to set theory. The complement of 0 is 1, and the complement of 1 is 0. Like I said, analogously, the complement of the null set is the universal set, and the complement of the universal set is the null set. So this is all great, but where are we going with this? How are we going to use these properties to help us write proofs? Because you know that's where we're going. We are always writing proofs in this class. Well, let's start with proving that for all A in a Boolean algebra B, the double complement of A is A itself. So let's write out our statement. Our statement here is simply restating what we were just asked to prove. That for all A in a Boolean algebra B, A's complemented is A. And what would a proof using Boolean algebra look like? Well, it's going to be a bit of a mixture between a set proof or a direct proof and one of our algebraic proofs, because honestly, Boolean algebra is pretty algebraic. So let's do a little bit of both, but we have to start with supposing B is a Boolean algebra. We can't do anything until we know that we say that B is a Boolean algebra. And we're also going to say that A is an element in our Boolean algebra. That makes life a lot easier because then, and this is where you're going to have to trust me a little on this one, we have to prove this one in a slightly different way than we're going to find ourselves proving the other ones, because this one is related more to the definition of what a Boolean algebra is. So we're going to say then A complement plus A is the same as A plus A complement. And this is by the commutative law. Commutative law. So you can see how this is similar to our algebraic proof in that one manner. And this is the same as 1 by the complement law for 1, or by the complement law. And we can also see that A complement times A is the same as A times A complement, which is 0. And the first is given by the commutative law again. And the second is again given by the complement law. So thus, here, and again, this one is more because it's related to what the definition of a Boolean algebra is. It says, thus, A satisfies the two equations with respect to A complement that are satisfied by the complement of A complement. It's a lot of complements of complements in this one. We can say from the fact that the complement of A is unique, complement of A is unique, we can conclude that the complement of A's complement is indeed A. And so I knew this one was a bit abstract, so I thought we would do this one together. And the other two examples are a bit more straightforward, and the one problem I gave you on the homework this week is definitely a lot more like examples 6.4.2 and 6.4.3. So what does 6.4.2 say? It says prove that for all A in a Boolean algebra B, A plus A equals A. So we're trying to essentially prove an identity here, right? So let's see where we're going to get started. So we're going to say our statement is that we want to say for all A in Boolean algebra B, A plus A equals A. And so for our proof, we have to start the same way. Suppose B is a Boolean algebra and A is in B. Then, and this is where it looks strikingly like our algebraic proofs, we would say A is equal to A plus 0, because 0 is an identity, right? So this would be by the 0, or sorry, by the identity law, right? And we could also write 0 as A times its complement. So we could say this is A plus A times its complement by the complement law. Okay, so we're moving forward. Now we're going to use the distributive law, but we're going to use it in a way that you're not used to seeing it quite as much. It's going to be similar to what we would do, but not quite the same. So don't think that Boolean algebra is going to work exactly the same as regular algebra. You need to make sure you're always looking at your properties for this one, because our distributive law here is going to say A plus A times A plus A complement. And that is by the distributive law. Again, Boolean algebra doesn't work exactly the same as regular algebra because it's all about logic. We also know that A plus A complement is the same as 1. So we get A plus A times 1, and this is by the complement law. Now we've got A plus A times 1, which is just A plus A, which is by the identity law. And we have shown what we set out to do. Let's see if 6.4.3 is just as straightforward. Six point 4.3 says prove that for all A in a Boolean algebra B, A times A equals A. So very similar to the last one. So this one we're going to have our statement. Our statement is going to say for all A in a Boolean algebra B, A times A equals A. So we're proving some of these laws that we're going to be using quite often. So our proof would say, okay, once again, suppose B is a Boolean algebra and A is in our Boolean algebra B. Then we need to show that A times A is equal to A. Well, let's start with A. A is the same as A times 1 by the identity law. All right, well, we can also write 1 as A plus A complement, and that is by the complement law. Now we can use that distributive law again, and we get A times A plus A times A complement. So in this case, our distributive law worked exactly the same as it does with regular algebra. So we know now that we have A times A plus A times A's complement is 0 by the complement law. And thus we have A times A plus 0, which is just A times A by the identity law. And we have shown what we set out to show. So I hope that you find Boolean algebra kind of interesting. We're not going to spend a ton of time on it. We do have one discussion post on it where I'm going to ask you to simplify some Boolean algebra expressions. I think it's actually just one expression, but it's a complicated expression. And I'm going to ask you to do that on the discussion post because you may actually run into that if you're doing work with logic circuits and other applications of Boolean algebra in your future career.